In this video, we're going to begin our discussion of global program optimization. Now, it turns out that in order to talk about global optimization, there's another topic that we have to deal with first, known as data flow analysis. Let's begin by reviewing the simple basic block optimizations, in particular constant propagation and dead cone elimination. So here's a little piece of code, and we'll notice that there's an assignment of a constant to x, and we know from our lecture on local optimizations that that constant assignment can be propagated forward to the uses of x if the basic block is in single assignment form. This is particularly easy to do. And then if the value of x here is not used anyplace else in the program, that statement is dead and can be deleted. So here's a simple example over a basic block combining constant propagation and dead code elimination. Now these optimizations can be extended to an entire control flow graph. So here now we have a non-trivial control flow graph. Remember, a control flow graph is a graph of basic blocks where the nodes are the basic blocks and the edges show the transfers of control between basic blocks. And so this first basic block here has a test in it, an if statement, and it'll go to one basic block if the test is true, and to a different basic block if the test is false. Now, in this control flow graph, we can observe that x is assigned a constant, and then down here there are uses of x. And in fact, in this particular case, it is going to be safe to replace this use of x by the constant 3. So just like we propagated constants in a single basic block, we can also, at least in some circumstances, propagate constants across entire control flow graphs. Now, it turns out that there are some situations in which it's not safe to propagate constants. So here again, let's observe that we have an assignment of x, an assignment of a constant to x, and down here we have a use of x, but we cannot replace this x here by 3. And why is that? Well, that's because over here we have another assignment to x where x gets the value 4. And the interesting thing about this example is that notice that x is only assigned constants. So x is assigned a constant here, and x is assigned a constant here. But this value of x down here is not known. We don't know which constant is going to be, because if we come from this path in the execution, then x will be 4, and if we come from this path, the value of x will be 3. And so we can't replace x here by either one of those values, and it's not safe in this case to propagate constants to this use of x. And so the question then is, how do we know when it is okay to globally propagate constants? Now, for constant propagation, it turns out there is a simple criteria. To replace a use of x by a constant k, we have to know the following fact, that on every path to the use of x, so every path that leads to the use of x, the last assignment to x is equal to k. So on every single path that goes to x, and this makes sense, I think, intuitively, we must have assigned the constant x along that path, and that must in fact be the last assignment to x on each path. Let's take a look at our example again, and I'll switch colors here. So here we have the assignment x equals 3, and down here we have the use of x. And now what we need to do is we need to check, in order to replace this x by 3, that on every path that arrives at this x, that reaches this x, that x is assigned 3 along that path. Well, there are only two paths. There's this path, and there is this path, and it's easy to see that this assignment is on both of those paths, and therefore the last assignment on both paths, on all paths, is x equals 3, and therefore we can replace this x by 3. In contrast with this use of x in this example, we have a path here where x is assigned 3, and we have a path here that reaches along this path. Let me draw the whole path, actually. And along this path, the last assignment to x is 4, and so we cannot propagate any constant value to this use of x. In general, the correctness condition that a variable is assigned the same constant along all paths to a use of that variable is not that easy to check, because all paths includes paths that go around loops, as well as paths that go through conditionals, as we saw in the example. So checking these conditions is done through a family of techniques called global data flow analysis that is designed specifically to check conditions like this. And essentially, global data flow analysis is called global because it requires an analysis of the entire control flow graph. Stepping back for a moment, there are many global optimization tasks that we would like a compiler to perform. Constant propagation, global constant propagation, is just one of those. Now, it turns out that all of these global optimization problems share several common traits. So first of all, the optimization always depends on knowing some property X at a particular point in the program. So we want to know some piece of very local information. So for example, is X at a particular point in the program guaranteed to be a constant? Okay, that's the property for constant propagation. Now, however, even though we want to know some local fact, something that's specific to a particular point in the program, proving this fact requires knowledge of the entire program, or at least the entire control flow graph. So as we saw in the case of constant propagation, to figure out whether X is a constant at a particular point in the program requires reasoning about all the paths that lead to that statement, and that is a global property. So reasoning about all paths, that could be a path from the entry point of the method all the way through loops and across conditionals to the particular statement. All right, so in general, that's a very hard problem to solve, and for certain kinds of questions, it's really extremely expensive to solve it exactly. The thing that saves us is that it is okay always to be conservative. So typically for these optimizations, and if we want to know some property X, then what we really want to know is either X is definitely true. So if we say that the property is true, then we have to be right. We can't make a mistake. But it is always okay to say that you don't know. So it's okay to give up and say we don't know whether the property holds or not, because in the worst case, we just don't do the optimization. If we can't establish the conditions that would mean it was definitely correct to do the optimizations, then we want to play it safe and not do the optimization. So having approximate techniques, or techniques that don't always give the correct answer to the questions that we want to ask, is okay as long as we are always right when we say that the property holds, and otherwise we just say that we don't know whether the property holds or not. To sum up, global data flow analysis is a standard technique or family of techniques for solving problems with the characteristics that we just discussed. And global constant propagation is one example of an optimization that requires global data flow analysis. And in the next several videos, we'll be looking at global constant propagation and another data flow analysis in more detail.